So it's good to see all of you. I thought there'd be a bit of a smaller turnout just because there's hubs on Saturday, but it's good to see you guys are still attending your physics tutorials. So good on you guys. So today we'll go over some more solids and fluids. And again, you guys have only had 3 lectures on solids and fluids, so you've only gone through about half the content. So I am going to cover all of solids and fluids today. This will be stuff that you haven't covered, so don't be too worried if you don't understand it. So our question number 1, we've got a horizontal pipe which has a cross-sectional area at point A of 0.3 meters squared. Just get a new pen. And the diameter of the pipe increases smoothly so that the cross-sectional of the pipe at point B is 0.8 meters. .8 meters square. And if water flows in the pipe at point A with a velocity of 4 meters per second, what is the velocity of the flow at point B? So this is point A, and this is point B. Okay, and so cross-sectional area 1, so we'll call this cross-sectional area 1, is equal to 0.3 meters squared. And the velocity, so V1, is equal to 4 meters per second. And then cross-sectional area 2 is, A2 is going to be 0.8 meters squared. And then V2 is our question mark. So we want to find out what the velocity is going to be at point 2. Okay, so what you need to understand is that the amount of liquid, the flow rate, so this symbol here is for flow rate. So flow rate, and then the equation is the amount of volume per second. Okay, per unit of time. So that's telling you how much liquid is flowing past each point. Okay, and if you've got a pipe, the amount of liquid flowing past point A will be equal to the amount of liquid flowing past point B. Okay, so there's the same volume running past point A and point B. Okay, so we can say that flow rate 1 will be equal to flow rate 2. Okay, so remember that the unit of volume is meters cubed, and the unit of time is seconds, right? So then you can also say that flow rate is equal to, so flow rate can also be equal to area times velocity. Okay, so the cross-sectional area multiplied by the velocity of the liquid. And so if you do the units for area, that's meters squared, right? And what's the units for velocity? Meters per second, right? So that's meters squared times meters per second. So m squared times m is m cubed over seconds. So you see they have the same units, right? So that's the same thing. So you can either say flow rate is the amount of volume per time, or the cross-sectional area multiplied by the velocity of the liquid. Okay, so here we've got the area and the velocity. So we're going to use this equation here. And so if flow rate 1 is equal to flow rate 2, what that means is that A1 V1, right? So this is flow rate 1 is equal to A2 V2. So flow rate 1 is equal to flow rate 2. And then we want to find out V2, so we're just going to rearrange this. So V2 is equal to A1 V1 over A2. Okay, so then you just put in the numbers, which is 0.3 times 4 over A2, which is 0.8. So that's going to be 1.5 meters per second. Okay, so what's happened to the velocity of the liquid? It's decreased, right? So as your pipe gets wider, as the pipe gets wider, the liquid is going to slow down because you now have more area. Okay, so, and that's going to be proportional. So if your cross-sectional area doubled, then your velocity would halve. Okay, and if it was the other way, say it was going this way, then if the cross-sectional area halved, then the velocity would have to double to maintain the same flow rate. Okay, so that's an important concept to understand. Cool. So we'll move on from that. Question 2, water flows with constant velocity through a pipe which runs up an inclined bank. The pipe is at an initial height of 1 meter and rises to a height of 3 meters. The cross-section of the pipe does not change, and the pressure of the water in the pipe at the height of 1 meter is 90 kilopascals. So what is the pressure of the water at the top of the incline? So if we have our pipe here, so the cross-sectional area stays the same, and oops. So this height here, the change in height is 1 meter. Okay, so we'll say that. Oh, sorry, no, my bad. So we'll say that this height here, so this is height 1 is equal. Oh, sorry, what am I doing? Getting confused. So this here is height 1. So height 1 is equal to 1 meter, and then height 2, h2, is equal to 3 meters, right? And then, so we've been told that the water flows with constant velocity, so that means that V1, so that means that V1 is equal to V2, right? And V2 is equal to V1. And the pressure at point 1 is 90 kilopascals, so 90 times 10 to the 3 pascals. And we know that the density of water of this liquid is 1,000 kilograms per meters cubed, right? Okay, so here you have to use this equation here. So P1 plus density times gravity times height 1. I'm going to write out space. P1 plus density times gravity times height 1 plus half density times velocity 1 squared is equal to pressure 2 plus density times gravity times height 2 plus half times density times V2 squared. Okay, so that is quite a long one, but it's not too complicated. Okay, so P1, this first one here, P1 and P2, that's the pressure at that point. Okay, so P1 would just be the pressure at this point here, and then this part here, the rho GH, that part is going to be, so this part here is the pressure, and then this part here is the potential energy that it has due to height. So potential energy due to height, right? Because remember, if you remember the potential gravitational energy equation, it's mgh. So this time we're dealing with a liquid, so we just have density times gravity times height, not mass times gravity times height. So this is the potential energy in the liquid at this point due to its height. And then this last part here is going to be the kinetic energy. So the kinetic energy due to its velocity, right? So this is similar to kinetic energy is equal to half mv squared, but this time because it's a liquid we're just using density. Okay, so and pressure is also a form of energy, because pressure comes from the liquid molecules like bouncing around and having molecular energy. Okay, kinetic energy at the atomic level, at the molecular level. So what that means is this is the total energy at this point here, at point 1, and the total energy is going to be equal, because remember energy is conserved, the total energy in point 2 will be equal to the total energy in point 1. So that's why we use this equation. The total energy in point 1 is equal to the total energy in point 2. Okay? So here, we know that the kinetic energy at point 1 and point 2 will be the same. So if they're the same, they're just going to cancel out, right? So we can get rid of this part here, because in our problem the velocity doesn't change, but the height changes, and we want to find out what the pressure is. So we want to find out P2 equals question mark, right? So now we're just going to rearrange this equation. So that's going to be P2. So P2 is equal to this part, so P1 plus rho GH1, so that's this part here, minus rho GH2 so what I've done is just minus rho GH2 from both sides to get P2 on its own, but at the same time I've just moved P2 over to the left. Okay. So you could decide to factorize it here. So you could say rho and G are common factors in both of these. So you could say P1 plus rho G H1 minus H2. So you don't have to do that, but it could be convenient for you if you want to. So then our pressure 1 is 90 times 10 to the 3 plus 1,000. Our density was times gravity, which is 10, and height 1 was 1 meter, and then height 2 was 3. So that should give you 70 times 10 to the 3 pascals, which is 70 kilopascals. Okay, so what's happened to the pressure is that the pressure has decreased at point 2, and that's because it's gained potential energy, right? So remember that the kinetic energy stayed the same, and then it's gained kinetic energy. So for these two sides to equal, the pressure at point 2 has to go down, right, to make sure to conserve energy, right? Okay, so we'll move on to the next one. So we have a tank of viscous oil emptying through a narrow horizontal pipe into the open atmosphere. You'd like to increase the volume flow rate at which the tank empties to 3 times its current rate. The pipe is initially 6 centimeters long, but you are able to adjust its length. How long should the pipe be? So here you've got the word viscous. So whenever you see the word viscous, you're going to use this equation. If you see the word viscous, then it's quite simple because you're always going to use this equation. And that's flow rate is equal to our difference in pressure multiplied by pi multiplied by radius to the power of 4, and that's over 8 times this symbol here, which is viscosity. So the viscosity of the liquid. Have you guys had the viscosity lecture yet? No. So if you say that a liquid is viscous, it means that it's like thick. It doesn't run very well. So if you think of, like, say, tomato sauce, it's not very runny, is it? Compared to water. Like, water flows a lot better than tomato sauce, right? So if you were trying to squeeze water out of a bottle, it's quite easy to squirt it out. Whereas if you were trying to squirt tomato sauce out of a bottle, it'd be harder, so you have to apply more pressure, right? So the thicker liquid is, the more viscous it is, okay? And this is the number that tells you how viscous a liquid is. And because water is has a very low viscosity, because it's very runny, so in most of our problems, we just assume that water has no viscosity, is a non-viscous liquid in most of our problems. So if they talk about water, in your problem, if they say water, then you can assume that it's just non-viscous. But in reality, it does have viscosity. It is viscous, but it's just that it's so little that we can just ignore it, just like we ignore air resistance when we're doing our mechanics problems. Okay. Okay. So we have our equation here, and remember, this flow rate can also be equal to delta V over T. So on your cheat sheet, you should also have this one here. So delta V over T. So this is flow rate, remember? Oh yeah, so I didn't even finish that equation. So it's 8 times the viscosity times the length. So the length of the pipe. Okay, so here we want to increase the volume flow rate, to 3 times its current rate. So let's say that the current rate is flow rate 1, okay? And we don't know what that is, okay? But we know that flow rate 2, so flow rate 1 is equal to current flow rate. But we know that, but we want flow rate 2 to be equal to 3 times flow rate 1. Okay? So now the value of flow rate 2 is 3 times flow rate 1. So what you're then going to do is, since flow rate is equal to this equation here, you're now going to replace flow rate 2 with this equation. So delta P2 times pi, and pi is just a constant, so it's not 1 or 2. So radius 2 to the 4th power over 8 times viscosity 2 times length 2 is equal to 3 times delta P1 times pi times R1 to the 4th power over 8 times viscosity 1 times L, the length 1. Okay? So, and remember that this is just 3 over 1 times this, so you can just move this up onto here. So you can say 3, like that. That's the same thing. Okay, so now we're going to cross out the ones that don't change. So delta P1 and P2, they don't change. So we can just cross those out. So delta P1 and delta P2 doesn't change, so we'll take those ones out. Pi is the same on both sides. And yeah, and so H's the same on both sides. Viscosity is the same because it's the same liquid. And then radius is the same because it hasn't changed. So the only thing that you're left with on this side is the L2. So that's going to be 1 over L2, because if there's nothing on the top, it just becomes 1, is equal to 3. So the only thing left on top is 3. 3 over L1. Okay? So then we want to find out what L2 is. So we're going to flip it upside down. So then L2 over 1, which is just L2, is equal to L1 divided by 3, and L1, so the initial length was 6 centimeters, right? So 6 centimeters divided by 3, so L2 is equal to 2 centimeters. Okay? So I'm going to say like these ones can be like a little bit hard because there's quite a few steps involved. But sometimes they can be like quite simple. Like you don't have to do all of this if you just understand the logic. So if there's a resistance, so whenever a viscous fluid is going through a pipe, there's going to be resistance from the pipe. So the longer that the pipe is, the more resistance there'll be to the flow. So what's happened, so you wanted to increase the flow rate. So what you did was you made the length of the pipe 3 times smaller, right? So we made it 3 times shorter, and that means there's less resistance to flow, and we were able to increase the flow rate. Okay, so you could have just said, and you can see here that our flow rate is inversely proportional to L, the length, because L is at the bottom. So if you were to double the length, so if you were to double something on the denominator, you'd end up halving the flow rate, right? So you could have just looked at this equation and said the flow rate is inversely proportional to the length. So that means that if I want to increase the flow rate by 3 times, I'll decrease the length by 3 times. Okay? Cool. A viscous fluid flows along a long horizontal pipe. The radius of the pipe is 3 centimeters, and the viscosity of the fluid is 3.0 times 10 to the negative 3 Pascal seconds. If the fluid pressure drops by 250 pascals over a 1 meter length of the pipe, what is the volume flow rate of the fluid? So again, you've got that keyword viscous, so you're going to use that equation that I just showed you before. So this is quite simple. First, we'll write down all the values that we've been given. So radius is equal to 3 centimeters, so we have to convert that into meters. So that's 3 times 10 to the negative 2 meters. Or you could just say 0.03, because there's going to be 2 zeros in front of it. Okay, and then our viscosity is equal to 3 times 10 to the negative 3. And then our change in pressure. So it says the fluid pressure drops by 250 pascals. So that's the change in pressure. Delta P is equal to 250 pascals. And the length is 1 meter. And what we want to find out is the volume flow rate. So question mark. Okay, so this is pretty simple. You don't have to rearrange anything. All we have to do is plug in the numbers. So delta P is 250. I'll just write out the equation first. So delta P times pi times r to the 4th over 8. Viscosity times L. So 250 times pi times r to the 4th, which is 0.03 to the power 4 over 8 times 3 times 10 to the negative 3 times our length, which is 1. So if you're just timesing it by 1, you don't have to put that 1 on if you don't want to. Okay, so that should give you 2.65 times 10 to the negative 2, which rounds to 2.7 times 10 to the negative 2 meters cubed per second. Okay, cool. All right, so number 5, a beaker contains a layer of glycerol floating on top of a layer of water. The glycerol has diffused an average distance of 2.0 millimeters into the water. How long has the layer of glycerol been on top of the layer of water? So this here is a diffusion problem. So diffusion is if you release, how can I describe it? So diffusion is the phenomenon where things spread out naturally. So if you put some dye into the water, initially it's going to be in the one spot, but after a while the dye is going to spread out all throughout the water, even if you don't shake it up, and that's because of diffusion. So the dye molecules have a random kinetic energy, so the molecules are moving around and eventually they'll spread out evenly, so that's diffusion. So you would have learned about that in your other papers. That's right, isn't it? Yeah. So the equation for diffusion is this is x RMS, so this is root mean square. So that just means like the average distance that the molecules traveled. Okay, so average distance traveled, and that's equal to the square root of 2 times the diffusion constant times multiplied by time. Okay, so D is your diffusion constant, so that tells you like how much that material will diffuse. And here we want to find out the time, so we're just going to rearrange that. So T is equal to x squared over 2D. And so x is 2 millimeters, which is 2 times 10 to the negative 3. And that's going to be squared over 2 times our diffusion constant, which is 2 times 9.3 times 10 to the negative 10. Okay. And that will give you 2150 seconds. So here you want your time to be in minutes. So you have to convert your answer, which is in seconds, into minutes. So you're just going to divide that by 60. And that will give you 35.84 minutes, which will just round to 36 minutes. Okay. Now number 6, so we went over this in our tutorial last week. So as long as the 2 points are at the same height and the liquids are connected, you're going to have the same pressure. Okay, so the only thing that's going to determine the pressure is the height. So when you're looking at these ones, you're going to go through these one by one. So we'll look at option A. P2 is equal to P5. So those 2 points are at the same height, so that will be true. Then we'll look at option B. Again, P2 is at the same height as P6, so that's true. Option C, P3 and P7 are at the same height, so that's true. Option D, P4 is going to be less than P2. So P4 is at a greater height. So remember that as you go higher, the pressure decreases, right? Because as you go deeper into the ocean, the pressure increases. And then so E, pressure 5 is less than P6, but that's not true because they're at the same height. So option E is your false statement. Okay, so question 7. Water flows in a pipe which is initially horizontal and then bends to point directly downward as shown in the figure below. So at point A, the water has a gauge pressure of 2 times 10 to the power 4 pascals. So we'll call that P1. And velocity at this point, so V1, is equal to 0.3 meters per second. And yeah, the velocity of the water is constant in the pipe, so that means that V2, so that means that V2 will be equal to V1, so that's also 0.3 meters per second. and we want to find out what the gauge pressure of the water at point B will be. So we want to find out what P2 is going to be. So P2 equals question mark. Okay, and we know that, so this is point A, this is point B, so then the difference in height is 1 meter. Okay? So we can say that this will be height 1, which is equal to 1 meter, and we can say that height 2 is equal to 0 meters. Okay, so if we set point B as the reference point, height 2 will be 0 meters. Okay. So now, again, you've got a non-viscous liquid, which is water. So now you're going to use this equation, the big long one that we showed before. So P1 plus rho GH1 plus half rho V1 squared is equal to P2 plus rho GH2 plus half rho V2 squared. Okay, so here the velocity doesn't change, so we can say that these two are going to cancel out, so we'll get rid of the half rho V squared, but we need the rest. So again, we want P2, so we're going to minus rho GH2 from both sides. So then P2 will be on its own. P2 equals P1 plus rho GH1 minus rho GH2. So that's P1 is equal to 2 times 10 to the 4 plus, so again we're going to factorize it, so rho G 1000 times 10 and H1 was, oh sorry, so what I forgot to say is that because H2 is 0, anything multiplied by 0 is 0. So here we can also cross out rho GH2 because density times gravity times height 2 is going to equal 0. So we don't need that rho GH2. So I'll take that out of here. So this is just going to be P1 plus rho GH1, which is 1 meter. So you don't have to have that 1 if you don't want to. And that's going to give you 30,000 pascals, which is, so there's 1, 2, 3, 4 zeros. So 3 times 10 to the 4 pascals. Okay. Sorry?
I got like, I don't know what number it is, 2 and all 2 zeros when I calculated it.
2 times, oh, it's plus, not plus 1,000. Yeah. Okay, so now crude oil flows through a long, straight, horizontal section of pipe which is 1 kilometer long, has a uniform cross-section, and a diameter of 1.5 meters. The volume flow rate of the oil is 4 meters cubed per second, and the viscosity is 7.5. What is the pressure difference between the beginning and end of this section of pipe? So you've got viscosity, so it's a viscous fluid. We're going to use that equation that we talked about before, the viscous fluid equation. And so we're going to write down our variables. So our first variable is 1 kilometer long, that's the length. So the length of the pipe is equal to 1,000 meters, right? And then we told that the diameter is 1.5 meters, but we don't want the diameter, we want the radius. So radius is half of the diameter, so that's 0.75 meters. The flow rate is equal to 4 meters cubed per second, and the viscosity is equal to 7.5, and we want to find out the pressure difference, which is delta P. Okay, so our equation is going to be flow rate is equal to delta P times pi r to the 4th power over 8 times the viscosity times the length. So we want to get delta P. So 8 viscosity and the length are going to go to the top here, and the pi r to the 4th power is going to come down to the bottom. Okay, so that's going to become flow rate. So 8 viscosity and L is going to go to the top, and that's over pi r to the 4th power, which is equal to delta P. Okay? So delta P is equal to our flow rate, which is 4 times 8 times viscosity, which is 7.5, times the length, which is 1,000, over pi times our radius, 0.75 to the power of 4, and that's going to equal 241,000 pascals, 241,444 pascals. So you want to turn that into kilopascals, so you're going to divide that by 1,000, and that will give you 240 kilopascals. So number 9, we have a non-viscous fluid flowing through a horizontal tube which has a downward bend and a constriction as shown in the diagram below. The ratio of the cross-sectional areas is 1 to 0.75, and the velocity of the fluid at point 1 is 2.30 meters per second. And you know the pressure at point 1 is the same as the pressure at point 2. You want to find the difference in height between point 1 and point 2. So this one here is actually a difficult one, so this should be in the advanced tutorial, but you guys are pretty smart, so I'll show you guys. So P1, we know that so here this is a non-viscous fluid, so if we have a non-viscous fluid, we're going to use P1 plus rho g h1 plus half rho v1 squared is equal to P2 plus rho g h2 plus half rho v2 squared. Okay, so we've got we want to find out the difference in height. So the difference in height is going to be height 2 minus height 1, right? So we're going to have to find some way to get both h's on the same side. And also we know that, so we'll write down the variables that we've been given. So we know that P1 is equal to P2. So what that means is that we can cross out P1 and P2 because they cancel out. And we know that the velocity, so V1 is equal to 2.3 meters per second, but we don't know what V2 is. So remember that in this equation we need to have V1 and V2, but we don't know what V2 is. But we've been given the areas, so remember we can do A1 V1 equals A2 V2. So we're going to figure out the V2 by using that equation. So then V2 is equal to, I'll write that here. So V2 is equal to A1 V1 over A2. So they've just given us a ratio, but you can just say A1 is equal to 1 and A2 is equal to 0.75. So A1 is equal to 1 times V1, which is 2.3, over A2, which is 0.75. And that's going to give you 3.0667 meters per second. So we're not at the end of our calculation yet. This isn't our final answer, so we're not going to round too early. We're going to leave at least 5 significant figures in that value. Okay, so now we've got V1 and V2. So we can start to rearrange our equation. So what we'll do is first we're going to minus. What are we doing? So we're going to minus half rho V1 squared from this side, from both sides. So that's going to be rho GH1 equals, because we're getting rid of this, is equal to rho GH2 plus half rho V2 squared. So that's this part here, minus half rho V1 squared, okay? And then what we're going to do is we're going to minus rho GH2 from both sides. So then we're going to bring this one over here. So that's rho GH1 minus rho GH2 is equal to half rho V2 squared minus half rho V1 squared. Okay? So now you can... Oops, sorry. I did that the wrong way. Oh, well, it doesn't matter. Yeah, let's just leave it like that. So this, now it's going to be H1 minus H2, not H2 minus H1. So it doesn't really matter as long as you get the difference. So we're going to factorize it now. So rho G, H1 minus H2. So this is delta H is equal to half, and we can factorize this as well. So half rho V2 squared minus V1 squared. So we can just, so this is, we can now, so that's basically rho G times delta H, right? Is equal to half rho V2 squared minus V1 squared. And then, so we're going to divide both sides by rho G. So delta H is equal to half rho V2 squared minus V1 squared over rho G. Okay. And then you've got density on the top and density on the bottom, which is the same. So that's a common factor. They're going to cancel out. So now you can just write half times V2 squared, which is 3.0667 squared, minus V1, which is 2.3 squared, over gravity, which is 10. So that should give you 0.206 meters. And you want to turn that into millimeters, so you're just going to divide that by the prefix for milli, which is times 10 to the negative 3. Okay, so that will give you 206 millimeters. Okay, sweet. So that's a bit of a tricky one, but hopefully you guys understood it. Right. I'll move on. So now our last question for this tute. A large tank contains oil with a viscosity of 7.5. The tank has walls and a floor which are 2 centimeters thick. But there's a small circular hole at the base of the tank, and oil is leaking through there. The fluid pressure at the base of the tank so that's 2 centimeters. So the fluid pressure at the base of the tank is 126 kilopascals. So at this point here, the pressure, we'll call that P1, is equal to 126 kilopascals, which is times 10 to the 3 pascals. And the radius of the hole is 1.5 millimeters. So this here, so not the full length, but half of it, half the hole, is going to be the radius, which is 1.5 millimeters. So that's 1.5 times 10 to the negative 3 meters. So that's your R. So R equals 1.5 times 10 to the negative 3. And again, so we know that the base of the tank is 2 centimeters thick. So now where the pipe is, so this is a bit of a tricky one because you've got a viscous fluid, and the actual pipe bit through which the fluid is flowing is going to be this part here. So this part here is the pipe, okay? So the length of this pipe is going to be 2 centimeters, which is the thickness of the wall, of the base of the wall. So this variable here, right, is going to be our length. So length is equal to 2 centimeters, which is 2 times 10 to the negative 2 meters. And we know that the atmospheric pressure, so this liquid is coming out through here, and the atmospheric pressure outside, so the atmospheric pressure outside, which we'll call P2, is equal to 101 kilopascals. So 101 times 10 to the 3 pascals. Okay. So, of course, if we have a viscous fluid, we're going to use that equation for viscous fluids, and that contains delta P, which is a difference in pressure. So we need to calculate the difference in pressure between this point and this point here. So that's going to be delta P is equal to 25 times 10 to the 3 pascals. Okay, so that's the difference between point 1 and point 2, or point 2 and point 1. And we want to know the volume flow rate. Okay, so it's just a matter of now putting the numbers in. Volume flow rate is equal to delta P times pi times r to the 4th over 8 L. So that's delta P was 25 times 10 to the 3 times pi times our radius, which is 1.5 times 10 to the negative 3, and that's to the power of 4, and that's over 8 times our viscosity, which is so they tell us the viscosity is 7.5 and our length is 2 times 10 to the negative 2. So that will give you 3.3 times 10 to the negative 7 meters cubed per second. Okay, so that last one is pretty easy, but the challenge is where the real challenge is interpreting the question correctly. So just realizing that this part here would be the pipe. Okay. So that's the end of the first tutorial. I'll be starting in 15 minutes for the advanced tutorial. All right. Thank you.
Huh?